So one property of element is that of effective nuclear charge. And what effective nuclear charge is if you think about it, the electrons, they are all surrounding the atoms, and they don't fly off into space because the electrons, they feel an attraction to the nucleus on the inside of the atom. Remember, the nucleus is where all the protons are. It's also where all the neutrons are, but the protons are important in this discussion because they are what are keeping the electron cloud, you know, in kind of this shape. Remember, the electrons themselves are all negatively charged, and so they're all repelling each other. They aren't going to want to get too close because, you know, negative and negative really repel each other, but the negative charge on the electron actually pulls them closer to the positive charge at the nucleus. But some electrons, they tend to feel a stronger attraction to the nucleus, and that's based on position. Electrons that are close to the nucleus, they feel more of an attraction than electrons that are further away from the nucleus. And so, and some electrons actually get in the way of other electrons from feeling that kind of attractive force. Okay, and so what this Z effective calculation is basically it's a calculation to assess how much a positive charge and any electron, any particular electron, quote unquote, sees based on the number of electrons that are in between it and the nucleus of an atom. And so there's a calculation in your textbook for calculating Z effective, but that calculation is a little bit cumbersome, and so we're going to use this essentially approximated Z effective, okay? So the approximate Z effective calculation goes like this. We're going to take all of the protons at the nucleus, so the entire charge of the nucleus, which is basically just all the protons, right? They all contribute a +1 charge. So all the protons at the nucleus minus the inner electrons, or the electrons that aren't in the outermost shell. Okay? So if we think about this for sodium, consider sodium. It's got a total of 11 protons at the nucleus. And we're saying that it has 10 inner electrons. And so the Z effective for sodium is +1. Now let's look at the periodic table to see why that is. So let me go over to the periodic table. Okay, the periodic table shows sodium right here at 11, right? Its number is 11. It's got 11 protons. If we think about the inner electrons, they're all the electrons that basically are contributing, that are identical to neon. So neon is our core electrons here, right? When we write our abbreviated electron configuration, it's neon 3s1. Well, that s1 electron on the outermost shell is the only outer electron. All the other ones are considered core electrons. And so any electron that is in a shell is blocked by all the electrons in the shells that have lower principal quantum numbers. So this outermost electron is blocked by all the electrons in the 2 shell, so and principal quantum number 2 and principal quantum number 1. And so that's where we get this calculation that we had right over here. So we have 11 total protons at the nucleus. There are 10 core electrons, right? Because there are 10 electrons in neon. And so we get 11 minus 10 equals +1. So this is another way to think about it. Remember, all of the protons are at the nucleus here. We also have some neutrons here too. But for helium, which is right here, okay, it's a little bit off my screen. I wonder why. Hold on. No. Okay, so helium's right here. It's got 2 electrons total. These electrons are both in the 1s shell, okay? So they're in the 1s shell. And so there are no electrons in between the electrons in the outermost shell. The outermost shell is the first shell. There's no electrons in between them to block them. So helium, essentially, the electrons feel the entire weight or pull from the protons at the nucleus, all the electrons in helium. And so the shell looks like this. We go to lithium, it's got an inner core shell, okay, but it also has one electron that's in the 2s subshell, the 2s shell, and then that electron right there would be blocked by the 2 electrons in the inner shell. Go to beryllium, it's got 2 electrons in the outermost shell. Both of those electrons are blocked by the electrons in the innermost shell. But remember, we are increasing the number of protons at the shell. We have 1 proton here, 2 protons there, 3 and 4. So beryllium only has 2 electrons that are blocking this +4 pull from the beryllium nucleus. So that right there indicates that this would have a higher effective nuclear charge. And then oxygen has all of these. Oxygen is in that same row. Oxygen has 8 electrons, 8 protons, right? So it's got 8 protons pulling all those electrons in, but only 2 of the electrons are blocking the outermost electrons. So we got 6 in the outermost shell. 1, 2, 3, 4, 5, 6. We've got 2 in this inner shell, 1 and 2, and so we have 2 electrons that are blocking these outer 6 electrons. And so Z effective would be greatest for oxygen, lowest for lithium. And so the trend for that, see, 2N shell. So if we look at the Z effective for these, we have +1 for lithium. For beryllium, we'll have +2. For oxygen, we'd have +6. So the trend for that is shown here. Essentially, the only trend for Z effective is as you move across a row, the Z effective, or the pull of the nucleus on those outermost electrons, increase.